Now we're going to use Ampere's law in a solenoid. We want to find the magnetic field inside this very long solenoid here. We have N winds of this wire per unit length. We have a steady current, I, travelling through the wire, and we'll give it a radius of R. Now let's start off with some general knowledge. We expect the magnetic field inside the solenoid to be parallel to the long axis. I've used the subscript I to indicate it's the magnetic field inside. Because it's parallel to the long axis, there's not going to be a radial component to this magnetic field, and there's not going to be an angular dependence either. From the right-hand rule, thumb pointing along the current, it follows that the magnetic field inside should point upwards. Outside, we expect our magnetic field to be vanishingly small. So this is what we know from general knowledge. Now what we'll do is put in an Amperian loop. We need to put in a loop so that current will flow through it. And we also need to put the Amperian loop in a position so that at least part of the loop is located where we want to find the field, that is, inside the solenoid. So we will put our loop here, inside and outside. And you can see the surface that it describes as well. We will give it dimensions W and L. Now the current that flows through each loop is I. The current that flows through each wire is I, and so the current that flows through this loop is I times the number of wires that go through this loop. Our current is equal to, the current enclosed, is equal to the current times the number of wires that go through the Amperian loop of length L. And now, the more tricky part. we need to integrate dl as we move all the way around the loop, and we need to take the dot product with the magnetic field at the same point. So what is this going to look like? Let's start at this point here. We're going to see what happens when we have an infinitesimally small loop element. Let's look at our dl here. We're going to move around in the direction that's given by the right-hand rule. So in this case, our current is actually traveling into the board. The surface here, of course, is parallel to the board, and our current is traveling into it. So that means that the right-hand rule gives us our integration direction as clockwise. So dl points this way at this point here, inside. The magnetic field vector is perpendicular. So the dot product is 0 as we move along here. As we move outside, we know now here the magnetic field outside is 0. So obviously the dot product here is 0 too. Going down the right side, there's no magnetic field. So B.dl is going to be 0 all the way from top to bottom, down that length L. Going left again down here, we have the same situation as we did at the top. The magnetic field on the outside here is 0. The magnetic field on the inside is finite, however, it is right angles to our length element. So the dot product is going to be 0. Finally, we move up the left side, and here the magnetic field is always parallel to dl. The magnetic field at this point points this way. So the dot product, B.dl, then simply becomes the algebraic product, B.dl. Integrate that over the length L and we get BL. Now we will use Ampere's law, and we can find out the value that this magnetic field takes. So the integral of B dot dl around this curve is BL, and this is equal to the current that goes through that surface. We'll cancel out the L's. So that gives us a magnetic field flux density of N, the number of turns per meter, times current. So this expression that we've found shows us that the magnetic field depends on the turn density and the current, and not on the position R within the solenoid. So it doesn't matter where you are within the solenoid, the magnetic field will always have this magnitude. So in summary, like Gauss's law, Ampere's law is always true, at least for constant currents. And it's useful when you have problems that have symmetry. Of course, if the problem doesn't have nice symmetry, we'll fall back on the Biot-Savart law. This is a lot of tedious summing involved to find the solution with Biot-Savart law, but computers are built for this job.